so now that we're past the second exam, it's going to get a little bit easier from here on out. It's like not so much quantum theory in itself, but just applications of it. And when I say applications, I mean things that you've seen before, things like Lewis structures. You've seen that before. It's just an application of quantum theory is all it is. We'll talk about bond energies and best for shapes, all that stuff in the coming chapters. In this chapter, chapter 9, right? We're in chapter 9 now, can you believe it? You're like, no, we can't. In chapter 9, we'll review Coulomb's law, which is going to be an underlying theme as we go on and on. We're talking about in chapter 8. We'll do something called lattice energy, which is just an application of Hess's law. And I gathered when we did Hess's law in lecture before, actually it wasn't too bad. It's a pretty straightforward topic. We'll talk about bond polarity, not to be confused with molecular polarity. It's a different kind of deal. We'll do Lewis structures. We'll probably start with Lewis structures today. And then we'll talk about bond energies. I've got a cool video to show you on that. If we get to today, great. If not, I'll show it to you tomorrow. When we get to molecular polarity, we have to talk about the Vesper shapes first. So we have to talk about tetrahedrons and trigonal pyramids and that kind of stuff. That'll be in chapter 10. So anyway, chapter 9 is kind of a cool chapter that's on some familiar ground. Okay, so something you haven't seen before with Coulomb's law. This is a mathematical statement of Coulomb's law. Excuse me. So what is Coulomb's law verbally? How would you explain it to me? Opposites attract, right? It's the dating game of chemistry, right? Opposites attract like charges repel. Well, maybe not the total dating game, but it's, you can think of it as sort of like, okay, two molecules are attracted to each other, or two ions are attracted to each other. This 1 over 4 pi epsilon, in physics, I believe the form of this equation changes a little bit, and they use some constant called K. If you've had physics before, I don't know, does that look familiar and sound familiar to you? If not, don't worry about it. So this 1 over 4 pi epsilon, okay, is a constant, okay? This 4 times pi obviously is a constant. This epsilon is called the permittivity constant. We will not do any calculations with this equation, but I'm just using it to describe how Coulomb's law works from a conceptual standpoint. Q1 and Q2 are the charges of the two particles. And R is the distance between them. Why don't they use D? I don't know why. They just use R for whatever reason. Okay, so the thing with Coulomb's law is that E is the potential energy between those two particles. So in other words, the more positive that E is, that means that there's a higher potential for them to want to come together if they are opposite charges. But conversely, if they're like charges, if Q1 and Q2 are both positive or both negative, then again, the higher the potential energy there, the more they actually want to fly apart. Right? So there's a concept there, that we should try to get to. Usually I bring a bungee cord. I forgot to bring it. That would have been a good one. Okay, so think about a rubber band, right? If you stretch it, okay, is there a high potential for it to want to come back together again? Yes, right. So if you're stretching things, you have a high potential for the opposite charges to want to come together. So the farther distance R is, so as this distance between the two objects, Q1 and Q2, increase for opposite charges, that means that that the E becomes less negative. Okay, so if Q1 and Q2 are both, one's positive, one's negative, the potential is going to be negative, but as R increases, it becomes less negative, meaning it becomes more positive, and the potential energy increases. Okay, so as R goes higher, all right, divided by a larger number, E gets lower. Conversely, if you have opposite charges, as R gets higher, E gets higher. Okay, so we could do. I have a worksheet I could give you later if you want to play with the calculations. But let's just in plain English, let's just say as opposite charges are farther apart, they want to come together. So opposite charges far apart, okay, there's that rubber band stretching, and as those opposite charges are far apart, they want to snap back together. Let's put it in the context of an atom and an electron now. Okay, as an electron is far from the nucleus, as long as it's still bound by the nucleus, okay, it wants to fall back down and emit a photon. The atom wants to emit a photon as a result. So it kind of goes back to the first law, you know, as potential energy is high, but then as the electron falls back down, that potential energy is released into the surroundings as in the form of a photon. All right, so it's sort of the same thing here. You know, electron is negatively charged, the nucleus is positively charged. Okay, so as the electron gets closer to the nucleus, the potential energy is released into the surroundings. Conversely, if you had two electrons coming in contact with each other, now they're both negative. Now as the distance between those two electrons gets smaller, okay, the potential energy gets higher. All right, in other words, the electrons want to fly apart. And that kind of goes along with the screening and shielding we were talking about before. All right, so I probably just spoke a bunch of gibberish and you're like, what did he just say? When it comes to an equation, I always like to think, what is it telling us physically, what's happening? What is the math telling us? All right, so you could just pick +1 and -1 for charge 1 and 2, and then play around with the number for R. You know, just pick a number, decrease it or increase it, and see what happens to the potential energy. Okay. So conceptually, it's just opposite charges coming together that decreases the potential energy of the system. Okay. If opposite charges are still far apart, that's a high potential energy situation. If two if two light charges are close together, that's actually a high potential energy situation. If they're farther apart, it's a lower potential energy situation. So just to try and paint it here. All right, here's R. Is this a really tense situation or a really relaxed situation? It's pretty tense, right? These guys want to go this way and that way, right? Same thing with two negative charges. They're like, I hate you and I hate you too, right? So they want to do this. Okay, so this is a high potential energy situation. So is this. Right, but as you get to opposite charges, okay, is that a high or low potential energy situation? This is a low potential energy situation. All right, these guys want to just do that. They want to come close together. Does that make sense? I hope. So as the distance r increases for light charges, you go from high to low potential energy. Okay, as the distance r between two opposite charges increases, you actually go to higher potential energy. So how does this affect the chemistry? When you form bonds, what you're doing is you're bringing electrons and protons together, excuse me, forming bonds. And this plays a role in both ionic and covalent bonding. Okay, so that's what we're going to talk about in this chapter. Okay, so there's something called lattice energy. And so this dives into ionic bonding. When salts form, they form what we call a lattice of cations and anions. Okay, it's when you look at a granular salt, are you seeing one cation and one anion together, or are you seeing gazillions and gazillions and gazillions of them? And the answer is you're seeing gazillions and gazillions and gazillions of them, right? You know, otherwise you wouldn't be able to see it with the naked eye, right? So you're forming this crystal lattice, and it forms a granule if it becomes large enough. That lattice has an energy to it. Okay, so here's your gazillions and gazillions of cations and anions. The blues and the greens are just opposite charge cation and anion. As they come together to form a lattice, all this heat is released, okay, out of the surroundings. Why is heat released? Okay, it's because you're going from going from positive and negative out here, okay, cation says, hey anion, I love you. I want to come together and hang out and marry you for life. That's what they say. Okay, so this is a high potential energy situation. Again, Coulomb's law, mathematically, you can calculate potential energy, but we're not going to do that. But just understand it conceptually, as these cations and anions come together, you release heat out into the surroundings. Why is that? Because of the first law, energy is conserved. Okay, you have to, as opposite charges come together and go from the green situation here to the black situation, okay, you are releasing heat into the surroundings because that potential energy is now met. Okay, so think of the long distance relationship scenario. How many of you haven't seen a movie where there's that situation, right? You know, two people living far apart, and then they finally get to live in the same house, and they're happy forever. So the movie goes. Okay. So going from a high to a low potential energy situation is what happens when ions form a crystal lattice. Now, in chapter 7, we were talking about electrons falling down into a nucleus, and instead of releasing heat, you released radiant energy. You released photons, right? But this is just heat being released. By the way, can anyone think of a reaction that might form a salt? Well, if you throw chlorine gas in a vessel with sodium metal, that chlorine gas will strongly oxidize the sodium metal, and you'll form sodium chloride salt. Okay, it's a really violent reaction. Okay, and the reason why is because all this heat is now being released out to the surroundings. Okay, so any questions on like what is lattice energy? Conceptually, Coulomb's law, you know, what is potential energy? Okay, it's the potential for light charges to come together, or excuse me, it's the potential energy for light charges to fly apart, or it's the potential for opposite charges to come together. Okay. Okay. So there's a process called the Born-Auger cycle, and it's used to estimate lattice energy of salts. And what you do is you combine known values of enthalpy to calculate the heat of the enthalpy of the lattice. Okay, and it uses Tesla's law. Let me just walk you through the process. So we want to form sodium chloride in this example. Okay, now when we're forming sodium chloride from its constituent elements, okay, the element form of sodium is the sodium metal, right? It's this formula. The elemental form of chlorine is a diatomic gas. Okay, and if we're forming 1 mole of that substance, so any solid plus 1/2 chlorine gives us 1 mole of sodium chloride, solid. So this plus this going equals to this is the formation reaction of sodium chloride. And do you remember what formation reactions are? It's the formation of 1 mole of a substance from its constituent elements. Okay, so forming 1 mole of sodium chloride would have to have 1/2 here for the chlorine. Okay, but to do that, you've got to go through a process to get there. You can't just go straight from here to there without breaking up electrons and protons and recombining them. All right, you got to have the transformation aspect. As Walter White would say, you got transformation. Anyway, okay. So going from this to this, we actually have to go up and then back down in potential energy. So it says here enthalpy H. Okay, really what we're talking about is going up in potential energy and then releasing potential energy down. So sodium and chlorine, first thing is you have to convert the sodium solid into sodium vapor. Okay, so there's a vaporization energy associated with it. You got to put energy in to do that. Okay, then to go from vapor and vapor to, you got to go from chlorine molecules to chlorine atoms. Okay, that requires energy as well. You got to break up those chlorine atoms away from each other. And so now you got gaseous sodium atoms and gaseous chlorine atoms, not gaseous chlorine molecules. And then from here, you got to ionize the sodium so that you form a cation. So going from sodium neutral vapor to sodium +1 gas, that takes that's the ionization energy of sodium. First ionization energy of sodium. Okay, but then from there, chlorine goes from neutral to -1. Okay, why are we going down in potential energy? Why are we going back down at that point? Or are we awake yet? Coffee, right? So how can we actually go back down in potential energy when chlorine gains an electron? Positive and negative, right? It's this situation. So here's this nucleus for chlorine. Here's this electron that's now going to be gained by the chlorine nucleus. Okay, and so now you're going to come together and actually go to a lower potential energy state. This is the electron affinity for chlorine. Okay, EA1, right, first electron affinity. And then, of course, once you combine the positive and the minus charges, okay, you get this big drop of potential energy that happens. Okay, and that big drop is because now you got positive and negative charges coming together. It's a big blowout of potential energy. So you got to go a little bit up and then all the way back down. Question: these are all positive energy inputs, but then these are all negative energies as you get the energy back out. Do you think lattice energy is going to be do you think the formation reaction is going to be positive or negative? It's going to be exothermic, okay, overall. All right, so sodium chloride wants to be sodium chloride. Sodium is just dying to get oxidized, and chlorine is all too happy to do it. Okay, so now you're going to, definitely get a negative enthalpy of formation from sodium chloride. Where do you think you could look up this value? It's in that table of enthalpies from chapter 6, right? So you could look that up. So this big dump out of potential energy as you go from cation and anion down to an actual solid crystal. This is called the lattice energy, right? So it's big. And the lattice energies vary depending on what the cation and the anion are. What are the size of the cations and anions? What is the extent of the charge and so forth. So let me walk you through the process. Okay. So what if we wanted to figure out, what if you were given all these reactions for the Born-Haber cycle for sodium chloride, and it was asking us, what is the lattice energy of these two ions coming together and forming a crystal lattice? What is this enthalpy? Okay. And so this is a showing of Hess's law, right? So all of these enthalpies are going to dump down, okay, and add up to this overall heat of formation of sodium chloride. So this bottom reaction is always going to be the heat of formation of the substance. The second reaction from the bottom will always be that of the lattice energy, and then you have all the steps of the Born-Haber cycle before that. All right, so going from sodium solid to sodium gas, there's a positive kilojoules for that. Right, that's going up in potential energy. Going from chlorine molecules to chlorine atoms, that's the chlorine bond energy. There's a bond energy associated with that. And because we're doing 1/2 of a chlorine molecule, you've got to multiply the enthalpy by ½ too. So that, again, that kind of goes in line with the properties of thermochemical equations in chapter 6. To ionize sodium, this is the ionization energy of sodium. Per 1 mole of sodium. This is the electron affinity for chlorine. This is now negative. Again, why is it negative? Electrons are being gained by a nucleus that's positively charged. Okay, so that's why it's negative. All right. How do we solve for lattice energy? So we know that, what we do know is that positive 108 kilojoules plus 1/2 times 244 kilojoules plus 496 kilojoules plus a negative, what is it, 349? Plus delta H lattice is going to equal to that bottom negative 411. So algebraically, does this look like a pretty easy problem? It does, right? So at this point, all we have to do is just rearrange this equation to solve for the lattice energy. All right, so delta H lattice is going to be equal to negative 411 kilojoules minus everything on this side. So I got 108 plus 1/2 times 244 So I'm just basically subtracting all of this over to the other side. And we do that, and we should get, if you got your calculator at your fingertips here, you should get negative 788 kilojoules. Right, you could have subtracted this to that side and added 411 to that side. Okay. Right, but ultimately you'd have to move the negative back over afterwards. So if that works easier for you, if that's how your brain works, then that's fine. Yeah, yeah, awesome.
You mind explaining where those numbers come from again? The 108?
Oh, so these are given to us, right? So you'll be given a problem, and you'll have all these numbers given to you, and you'll just have to know to rearrange it.
Like I said, it represents like ionization energy 1.
Right. So you might remember in chapter 8 last week we were talking about ionization energy of various elements. So what they've determined through many experiments is that it takes about 496 kilojoules to ionize 1 mole of sodium. So they're just literature values that you have to be given. Same thing with electron affinity. Yeah. So yeah, these have to be given to you from tables or literature from somewhere. Okay. All right. So if I gave you this problem and I said, hey, calculate the lattice energy of sodium chloride given these values, could you do it? And I think you could. Right. It's a pretty simple problem. You just got to rearrange algebraically. The math. Gotta love it. Okay. So again, what is lattice energy? It's the energy that you get that's released, okay, when a cation and an anion come together in a salt. Yeah, that's what the lattice energy is. And I should mention it's the energy released when you form 1 mole of that salt from a cation and anion. Okay, let's do another one.
Can you repeat that one more time?
Yeah, so the lattice energy is the energy released or consumed. Okay, but usually the cations and anions coming together is going to be negative. It's the delta H is the energy, the lattice energy is the heat released when you get a cation and anion forming a salt. Right? When they form together to form that lattice of cations and anions.
So it should always be negative, right?
It should, yeah. I mean, I can't think of any salts where the lattice energy would be positive for a salt. I mean, you get cation and anion coming together, it's always going to release potential energy out. It's always going to be exothermic. So, all right. Let's do another example. I think you could use one. So calculate the lattice energy of magnesium chloride using the information below. All right, so here you've got a bunch of reactions listed. It kind of shows it to you in a slightly different way now. It doesn't have the lattice energy reaction written in here. Okay, so you got the vaporization, you've got the bond dissociation of chlorine, you've got the first and second ionization energies for magnesium. Okay, and then you've got the first electron affinity for chlorine, and you've got the heat of formation of magnesium chloride. So let's go ahead and rewrite this in the way it was written for the sodium example, and I think it'll look pretty similar. Alright, so we got the first reaction there. I'm really just going to rewrite those, but I'm going to add the lattice energy reaction in there. Okay. Okay, so we got the delta H of plus 147.1. Then I've got the half chlorine. For simplicity, I'm leaving off the units for now. Let's see, magnesium gas. I'm going to call that ID1, okay, for magnesium.
Why?
Well, if you're ionizing magnesium from neutrinated +1, that's the first ionization energy, right? This number 738, it was in that table from chapter 8 when I was pointing out the trends in the ionization numbers. You can always go back to that if you want, but that's where that's from. Here's the second ionization energy. Not surprising, it's about double the first. When I wrote the reactants out last week, I included the free electron, but we don't have to write the free electron. Okay. Let's see, and the chlorine vapor gained an electron. So that's electron affinity of negative 349. All right, and then the heat of formation is always written at the bottom. And that was negative 641. Okay. What reaction goes here?
Lattice.
Lattice energy. Right? The question is, what is it? So what reaction goes here?